All right, to start our discussion today, we're going to look at a demonstration here online. You can see it's fet.colorado.edu. Basically what I'm going to do is I'm going to take some gas particles and I'm going to use this bicycle pump here and I'm going to pump some gas into this space here. Okay, and when I do that, you can see there go the gas particles into, and I'm going to do it a few times here just to get a bunch of gases going. Okay, and you can see that as those particles of the gas are hitting the walls of the container, notice that that is increasing the pressure. So if I add even some more gas to it, see that pressure right here? See what that does? See how that went up even more? Now what we're going to do is we're going to hold the temperature constant, and I'm going to change the volume of this container. So notice my pressure right now says 30 atmospheres. And again, that's based on those particles, those gas particles hitting the walls of the container. And what I'm going to do is I'm going to move this. See this handle right here? I'm going to move it out a little bit farther. And what I want you to focus on here is the pressure. What happens when I make the volume bigger? Well, what do you think is going to happen? Is the pressure going to go up? Is the pressure going to go down? Or is the pressure going to stay the same? Let's see, I'm going to move this out a little bit. The pressure was 30, and what happened to the pressure? The amount of pressure went down. As the volume of the container gets bigger, let's make it even bigger now. What happens to the pressure inside of it? The pressure goes down. Okay, and if we take that same container, and now I'm going to make it significantly smaller, so right now my pressure is 22.2 atmospheres. Now I'm going to make it a lot smaller. So now we're making the volume go down. What's the pressure do? As you can see here, the pressure went way, way up. Okay, and you can kind of see it there that the gas particles have less room to move around in, so they're hitting the walls of the container more often. And the more often they hit the walls of the container, the greater that pressure is. So we can see that when you increase the volume of a gas, the pressure of the gas goes down. And when you decrease the volume of a gas, the pressure goes up. Okay, and what that leads to is it leads to the idea of what is called Boyle's law. Okay, and there's a few different laws that we're going to learn dealing with gases. And one of them is the relationship between pressure and volume. And we've already seen it. We just saw Boyle's law in action. That as the volume of a gas gets smaller, the pressure goes up. So when the volume goes down, the pressure goes up. Okay, and that is what's called an inverse relationship. When one thing goes down, the other one goes up, and it's represented by this, that the volume is related to 1 over the pressure. Not equal to in this case. You can see that sign there does not mean equal to. Okay, there's a relationship between the volume and the inverse pressure. So when the volume goes down, the pressure goes up. Think about the little trick that you like to do with a water bottle, where you take a water bottle and you squeeze it really, really tight. You're decreasing the volume inside the volume of that water bottle. And then what do you do with the lid? You kind of point it at somebody, and then you go shooting off into the sky. You obviously don't point it at somebody, hopefully not, okay? But as you do that, you're increasing the pressure inside of there because you've decreased the volume. Okay, now mathematically, this is the equation for Boyle's law. P1V1 equals P2V2. And the ones mean the initial pressure. So think about your water bottle. The initial pressure is just regular atmospheric pressure. Your P2, your final pressure, is after you've squeezed that bottle to make that volume really, really small, what's that pressure done? So these over here, these are your initial values, or this is what you're starting with, the initial pressure and the initial volume. And P2 and V2, those are your final. So after you've made some change, what has the volume done? What has the pressure done? Okay, let's look at an example of this. Let's use that water bottle from before. Usually water bottles are about 355 milliliters, in volume. And the pressure inside is regular atmospheric pressure, which is just 1 atmosphere. Let's say I take that water bottle and I squeeze it so tight that it goes from 355 milliliters down to 216 milliliters. Okay, and we haven't changed the temperature or anything else. We haven't added any more gas to it. Now we want to know, what's the pressure inside the bottle? Now that we've reduced that volume, what's the pressure? So remember, P1V1 equals P2V2. So our initial pressure, the pressure we started with, was 1 atmosphere, so that's our P1. Our initial volume is the 355 milliliters, and that's equal to the final pressure. Now that's our unknown. That's the one we're trying to find. Okay, and then our final volume is the 216 milliliters. So basically, again, using algebra to find P2, we simply have to divide by 216. So we can see that here, that I took 216, I divided, moved it over to the other side. So I take 1 times 355 divided by 216, and the final pressure inside of there is 1.64 atmospheres. So what that means is it means that if you take a water bottle and you can take it from the 355 milliliters down to 216 milliliters, you've increased the pressure from 1 atmosphere to 1.64 atmospheres. Okay, let's look at a couple more examples. Example 2 says a metal cylinder holds 50 liters of oxygen gas. Now, sometimes as I do these, I kind of like to go through it and kind of identify things. So 50 liters of gas at 18.5 atmospheres and 21 degrees Celsius. And I think, wait a minute, why is that 21 degrees Celsius there? I thought he was only talking about pressure and volume. Okay, what volume will the gas occupy if the temperature is held constant while the pressure is reduced to 1 atmosphere? Okay, notice in this example, temperature is mentioned. But then I do say later on, temperature is held constant. Okay, why did I put it in there then? Just to mess with you, just to make you think, wait a minute, why is that temperature there? Okay, for Boyle's law to be correct, the temperature can't change. And that's an important concept, is that Boyle's law, this P1V1 equals P2V2, only when temp is held constant. Okay, we're going to talk about temperature in our next video. For this one, there cannot be a temperature change. So again, why did I put that 21 degrees Celsius there? Just to make you think a little bit. And then when it says temperature's held constant, you're like, oh, no, I can still use Boyle's law. So our initial pressure, so remember, we're going to use Boyle's law, P1V1 equals P2V2. Our initial pressure is 18.5 atmospheres. That's what we're starting at, right? Our volume is 50 liters, 50.0 liters. Our final pressure, it says the pressure is reduced to 1 atmosphere. So our final pressure is 1 atmosphere. And therefore, what must our volume be? That's our unknown. What volume will the gas occupy? So I'm going to take 18.5. I'm going to multiply by 50. And then to get that V2 by itself, I've got to divide by 1. So divide by 1. So V2 equals 925 liters. And again, let's think about that. The pressure was 18.5, and it was in a 50-liter container. To get that pressure to go all the way down to 1 atmosphere, you got to make that container way, way bigger. Okay, and that's what happens. You're going from 50 liters to 925 liters. All right, one more example. Oh, no, sorry, there's a couple more examples here. 2 more examples. So the gas pressure in an aerosol can, like when you're spraying hairspray or you're spraying, just something you're spraying like some Scotch Guard. Usually when it's full, the gas pressure in an aerosol can is about 1.50 atmospheres. And let's just say it has a volume of 6.23 liters. That's a pretty big aerosol can. Okay. The pressure, though, is changed to 1,352 millimeters of mercury. What will the new volume be at constant temperature? Again, you see that constant temperature there. That means that, yes, we can use Boyle's law. P1V1 equals P2V2. The issue here, and hopefully you caught it, is that pressure is in atmospheres, and that pressure is in millimeters of mercury. Okay, so if the pressures are in different units, which they are, they must be converted to the same unit. It doesn't matter which unit you convert to. You can convert the atmospheres to millimeters of mercury, or the millimeters of mercury to atmospheres, but they have to be consistent. Okay, you must have consistent units in here. So, just for ease, I'm going to convert my atmospheres to millimeters of mercury. So I'm going to take 1.5 ATM, and I know that 1 atmosphere equals 760 millimeters of mercury. 760 times 1.5 is 1,140 millimeters of mercury. So that is now my initial pressure. Because remember, these two are the same thing, they're just in different units. So my initial pressure is 1,140 millimeters of mercury. My initial volume is 6.23 liters. My final pressure, here it is again, 1,352 millimeters of mercury. And my final volume is what they're asking us for. So just like the last problem, to get V2 by itself, I'm going to have to divide by 1352. So I'm going to take 1140, I'm going to multiply by 6.23, and then I'm going to divide by 1352. And I get an answer of 5.25 liters is equal to V2. Okay, now does that make sense? Well, what did the pressure do? The pressure went up, so if the pressure went up, the volume had to have gone down, which is what happened. The volume went from 6.23 to 5.25 liters. Okay, last one. Okay, a gas under 6.25 atmospheres of pressure occupies a volume of 22.4 liters. If the volume is increased to 37.4 liters, what will the pressure be in torr at a constant temperature? So again, there's our constant temperature. So our initial pressure, 6.25 ATM. Our initial volume, 22.4 liters. The pressure is what they're asking us for, so P2 is what we're looking for. And then our final volume is 37.4 liters. So P2 is going to equal 6.25 times 22.4 divided by 37.4 equals 3.74 atmospheres. And again, guys, when you do the math here, notice that when you put that 37.4 liters on the bottom, the liters cancel. And so the units that you're left with are atmospheres. So notice they say, what will the pressure be? But then they want it in torr. So we've got our final answer, but it's in atmospheres. So we do need to check and make sure are our units correct. And in this case, they are not. So what do we have to do? 1 atmosphere equals 760 torr. So we take 3.74 and we multiply by 760 and we get 2,800. This only has 3 digits, so we're going to go 2,840 torr. Even though the calculator answer is 2,842, with those 3 digits, my final answer is only going to have 3 digits as well. Okay, so 2,840. Okay, so Boyle's law is the relationship between pressure and volume when the temperature is held constant. When one goes up, the other one goes down. There's an inverse relationship between the pressure of a gas and the volume of a gas, okay? And so anytime you think about Boyle's law, again, I always try to think of an example. So whenever I think about Boyle's law, I always think of the water bottle. Okay, taking the empty water bottle and squeezing it and increasing the pressure inside of it, and then taking that lid and loosening it really quickly and thinking of it shooting up into the sky.